differentiate the given implicit function with respect to x. Right. See, we have seen differentiation with respect to x and with respect to y. It's a little bit confusion we may have. So where we may get confused. So I have a x and y. If I differentiate with respect to x, what we get? Differentiate with respect to x. Then we get dx by dx. The same y we get dy by dx. So dy by dx stands dy by dx, but dx by dx we get 1. If suppose I do with respect to y, then what we get? We get dx by dy, and for y we get dy by dy, whereas dx by dy stands as dx by dy, but dy by dy becomes 1. This we must have some confidence in this particular thing, some clarity. If you have a clarity, then we can move on to the next problems, right? So given sin of xy plus x by y equal to x square minus y. So I am going to do differentiate with respect to x. So sin of xy differentiation with respect to x, I feel it as sin x. Sin x differentiation is cos x. So which is nothing but xy. But it's not x, so I have to do differentiation with respect to x. Plus I have in a u by v form. V u dash differentiation of x with respect to x is 1 minus u v dash, which is nothing but dy by dx whole divided by v square. We have y, so we get y square equal to x square differentiation with respect to x, 2x minus y differentiation with respect to x, dy by dx. Now take y square as LCM and simplify. So if I take y square as LCM, I get y square cos xy into dy by dx of xy can be rewritten as x into dy by dx, because I am finding derivative of the particular thing, plus y into dx by dx, which is nothing but 1, plus y into 1 is y, minus x into dy by dx, which is equal to 2x minus dy by dx. I have here denominator y square. If I transfer to right side, we get into y square. Now take dy by dx common in this all particular things. So if I take dy by dx common, y square cos xy into x. So I can write it as x y square cos xy. Next, and we don't have here any other dy by dx, and we have here dy by dx. So I took dy by dx outside, minus x remains. Again here we have dy by dx, which is minus, transfer to left side becomes plus. So plus dy by dx into y square. So I can take dy by dx common. The rest of the thing is nothing but y square, which is equal to 2x into y square, 2x y square, and y square cos xy into y. So transfer right side, minus y cube cos xy. Still y left alone, but yeah, we have y left alone. So take the y to right side, we get minus y. Now dy by dx is equal to 2xy square minus y cube into cos xy minus y by xy square cos xy minus x plus y square, which is the dy by dx differentiation of the given function with respect to and logarithmic functions. Yeah, we are going to discuss exponential and logarithmic functions. See the functions which are in the form of a power x. If I take y is equal to a power x, so y we can write it as f of x, right? The function written in terms of a power x, where a is greater than 0. So what we consider a is greater than 0. Those type of functions are called general exponential functions. What are those? General exponential function. So how they behave? The behavior of exponential function depends on a. So if the value of a is greater than 1, they behave in one manner. If the value of a lies in between 0 and 1, then they behave in another way. So why? Suppose you take 2, so it power rises frequently. 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 16. Where the value, the power, if the power increases, the value of the function also increases. If the value, if this one lies in between 0 and 1, then what is going to happen? So suppose if I take 1 by 2 whole power 1, which is 1 by 2. So 1 by 2 whole power 2, which is nothing but 1 by 4. 1 by 2 whole power 3, which is nothing but 1 by 8. So 1 by 2 whole power 4, which is nothing but 1 by 16. So we know that if the denominator increases, the value of the fraction decreases, right? See, the value of x frequently increasing and the value of y, which is nothing but the value of function, decreasing. So it behaves in two ways. If the value of a is greater than 1, the exponential function acts as increasing function. If the value of a lying in between 0 and 1, it's lying in between, we are not able to take, we are not taking a value as 0 or 1. We are just taking the values which are lying between 0 and 1, right? Then the function acting as decreasing function. If suppose I take the value of a as 1, then what happens? If the value of a as 1, then if I take values of x, so I take a 1, I got 1, I took 2, I got 1, I took 3, even I got 1, I took power 4, even I got 1. So it does not depend on the value of x. The function does not depend on the value of x, but whatever the value you substitute, even 0, we are getting a number 1. So which is nothing but a constant function. So for a value 1, the exponential function acts as constant function. A value more than 1, it acts as increasing function. If the value a lies in between 0 and 1, it acts as decreasing function. This one, constant function. Let me draw graphs of these particular things. See, if I take a as greater than 1, a as greater than 1, right? This stands for x-axis and this one y-axis. See, whatever the values you substitute, whether it is a positive values or it is a negative values or it's 0, for value of x 0, it exists. If anything power 0 is 1, right? Except 0, right? So if it is a positive or it is a negative, the function exists. So if I take a negative values nothing but a power minus infinity. So then what we get? 1 by a power infinity. So 1 by a power infinity. So 1 by a power infinity. So what a power infinity is nothing but approaches to infinity. It is approaching to infinity, where the value of x approaching to infinity. I am discussing about a power infinity. A power infinity approaches to infinity. Then 1 by infinity which approaches to 0. So it approaches to 0, starts from 0, where the values increases. So from negative to 0, if the value magnitude increases but the value of the particular thing decreases, means I have here minus 10, next to minus 9, minus 8, these are called magnitudes, right? So if that value if the value increases, its particular number value decreases. Suppose I have here minus infinity. Now its value I am going to decrease I am approaching minus infinity minus 1, right? Likewise, then minus 10 minus 1, minus of 10 minus 1, minus of 10 minus 2, minus of 10 minus 3. Like these values, I am approaching in this way. So minus 1, minus 2, minus 3, minus 4. Likewise, if I am approaching 0, the value increases. So if I approaches to 0, anything power 0 which is nothing but 1, I get the value of y as 1 and it frequently increases. But it does not touch 0 because anything power will never equal to 0. So this is a graph of the function a power x when a is greater than 1. Now you see the same thing if you apply for a lying in between 0 and 1. So what happens for more value? See, 1 by a we get 1 by a because we consider which is lies as a fraction. So if suppose I have taken 1 by a, so power something which is nothing but x. I consider least value. For the least value we get 1 by a value more, nothing but what we get 1 by a power infinity, sorry, a power x. For least value of x we get the maximum value for the function. For more value of x we get least value of the function, right? So for least value it will be maximum and it decreases and goes on. It does not meet value 0. So again at x value 0 it touches y axis at a point 1. So where it touches at 0 comma 1, at 0 comma 1, right? So this is the explanation for exponential function. Now we move on to the properties. What properties we have? We have learned these properties in lower classes, which is nothing but a power x whole power some y you take, we can write it as a power x into y, a power m whole power n, which formula we have learned, a power m into a power n, what we can rewrite as a power m plus n, a power m plus n, still a power m by a power n, which is equal to a power m minus n, a power minus x can be written as 1 by a power x. Likewise, these are all properties once we have to recall. Now, the domain and ranges of the given function. What are the domain and ranges? Domain specifies its x values. See, so in its domain we have all x values, but in its range it is started at some positive infinity to the least value 0, but 0 does not exist. So we got only positive values. For all the values of x it exists. So domain of the given function is all real numbers. Range of the given function is 0 to infinity. Both are open because we are not getting for any value the value of the function as 0. Next, we shall move on to logarithmic functions. So what are logarithmic functions? The inverse of the given function is nothing but logarithmic function. Inverse of the given function. Inverse, I have a power x. If I take a power x as n, so I want to define x. X is equal to log n to the base a. So as usually we use this n as y. So I replace this n as y. Now we got x is equal to log y base a. X is equal to log y base a. So we want to define the functions always in terms of x. So what we do, we interchange the values of x and y. So we get f of x, which is nothing but y, is equal to log y replaced by x base a. So these type of functions are called logarithmic functions, general logarithmic functions, right? Now in these general logarithmic functions, so what is its domain as well as what is its range? See, I have taken this particular thing as a function and I defined its inverse. So if I define its inverse, so how it behaves, its domain becomes the range of a power x. So the domain is nothing but 0 to infinity. So logarithmic function is always defined for positive numbers. So I have to mention log of x base a where x is greater than 0. Again, its range. What is the range? So for the range of logarithmic x, log x function is nothing but domain of exponential function. What the domain we have? R. So range of the function is nothing but all real numbers. So this is the logarithmic function, how it behaves. So now you see x and this one as y. For x and y. Again, this one also depends on the values of a. If a value greater than 1, strictly it acts as increasing function. If a value less than 1, it acts as decreasing function. If a value is greater than 1, for smaller value we get smaller. For greater value we get greater. So the function, the graph of the given function will be like this for a greater than 1. Now for a less than 1, so this will be acts as this. Now, so where we get the meeting point where the graph meets x-axis. So here the value of y is 0, the value of x is 1. So where we get the value of y 0, if the value of x is 1, we get the value of y as 0. Why? We have learned in previous classes, logarithm of 1 to any base is always gives 0. Logarithm of 1 to any base is always gives 0. Nothing but the value of x I consider as 1, then we got it as 0 irrespective of a. See, so logarithmic function meet x-axis and it lies in first and fourth quadrants. But exponential function lies in first and second quadrant. So what is the common for both the functions? First quadrant. The exponential functions as well as logarithmic functions lies in the common portion is nothing but the first quadrant. Now we have learned about a general exponential functions as well as general logarithmic functions. So when we get exponential function, if the basis, the value of a, if it becomes e, what we call, if the value of a becomes e, so y is equal to e power x. This we call natural exponential functions. What we call natural exponential function. If here logarithm of x to the base a, if a is replaced by e, so we get log x to the base e. So these type of functions are called natural logarithmic functions. This can be written as log x. We don't mention any base. It gives the base as e, or we can write as ln x. So in this way we indicate the logarithmic functions. So in logarithmic functions, here also we have a properties. Those properties are nothing but what we have learned in previous classes. So we learned that log x plus log y equal to log of xy. Log x minus log y equal to log x by y. Next, log x power m, which is equal to m into log x. So now interrelation of a logarithmic and exponential. So I have a function like a power x. A power x. So how we can rewrite this one in terms of exponential as well as combination of exponential and logarithms. So we know f inverse whole inverse is nothing but equal to f. Suppose if I consider this one as a function, I am converting this function in terms of logarithm by applying logarithm. So if I apply logarithm, means if I took its inverse, log of a power x. So log of a power x. Now again I am applying its inverse. What is the inverse of log? Exponent. So exponent inverse is logarithm, logarithm inverse is exponent. So again I am applying exponent, then we get e power log a power x. So first inverse, second inverse. So what we can say, a power x is always equal to e power log a power x. E power log a power x. In general, what we can say, if I have a power log x and I have a base a, if base of logarithm and base of exponential are same, that is nothing but equal to the value is nothing but equal to the number, which is nothing but x. So here e and the base of log is e, so what we get? A power x. So by doing few problems, we just use this results, right? So we derive few formulas. First one, finding limit of 1 by x. Limit 1 by x. So we are extending to 0. Limit 1 by x. We are extending to infinity. So in this case, extending to 0. So if I am finding extending to 0, first I have to check whether the limit existing or not. So at 0, I am checking. So if I am going to check at 0, I have to find its left as well as right limit. So which is nothing but limit extending to 0 minus 1 by x. Right limit extending to 0 plus 1 by x. See, if I take limit extending to 0 minus, which is approaching 0 from left side. So nothing but the value minus 0.00000001. Now it's reciprocal. If I take its reciprocal, what we get? 1 by 0.0001. Just for example I took. So now what I get? Minus 1, 2, 3, 4, 5, 6, 7. I have 7 zeros. I get 1 after 7 zeros, right? So this much value. But it's not the nearest one. Still we can go for nearest by taking millions of zeros. So we can express this one as the least negative integer, right? The least negative number. Instead of saying integer, we can say least negative number. So which is nothing but minus infinity. So what we get? Limit extending to 0 minus 1 by x, we get it as minus infinity. Whereas going for limit extending to 0 plus 1 by x, plus the same if it is plus, right, from right side. From right side it is approaching 0.00000 something 1. Then what we get? We get in terms of plus. In terms of plus. So we get plus infinity. So limit exists if left limit and right limits are equal. But here left and right limits are not equal. So we say here does not exist. So limit of 1 by x, whereas extending to 0 does not exist. Now going to extending to infinity. As extending to infinity, infinity plus and infinity minus. See, approaching infinity from right side is same as approaching infinity from left side. Yes, then which is nothing but equal to infinity only. So if it is infinity, 1 by x will tend to 0. If we extend to infinity, the reciprocal of infinity is 0. So what we get? Limit extending to infinity 1 by x, we get it as 0. Some binomial expansions are there. Binomial expansions and statements, results, what we call. That I have given, right? Binomial expansion. What is the binomial expansion of x plus a whole power n? So lastly we learned nc0 x power n plus nc1 x power n minus 1 a power 1 plus nc2 x power n minus 2 a power 2 plus and so on plus ncn a power n, right? So this binomial expansion, we are going to expand for any integer. If suppose I have a 1 plus x, what most frequently we use 1 plus x whole to the power of n. For x, modulus of x is less than 1, modulus of x less than 1, and the value n for integers we learned. So for any integer, just we are replacing this n as fraction. For integers we are using this. For any power, instead of saying any integer, we can say for any power. So we can go for one of the fraction. So if n acts as a fraction, a rational number, if n as a rational number, then what happens? So 1 plus x whole power n can be written as 1 plus nc1 x plus nc2 x square plus nc3 x cube plus and so on. So what is this nc1, which is nothing but n. What is nc2? N into n minus 1 by 2. What is nc3? N into n minus 1 into n minus 2 by 3. Just we can go with the formulas, which is nothing but nc3 n factorial by n minus 3 factorial into 3 factorial. So what we get? N factorial can be written as n into n minus 1 into n minus 2 into n minus 3 factorial by n minus 3 factorial into 3 factorial. So n minus 3 factorial gets cancelled. We get here 3 factorial. So in the same way 2 can be written as 2 factorial. So and so on. What we get next one? N into n minus 1 into n minus 2 into n minus 3 by 4 factorial. So in that way we expanded this. For any integer, na? So for any integer, what we have? Power n we have, we substituted n. If we have x, we can substitute x. We have something, we can substitute that. Suppose we have a power as 3 by 2. If I have a power 3 by 2, in place of n, I substitute here 3 by 2. That represents for any number, for any index. Okay. Now e power x and e power 1 values we have given 1 plus 1 by 1 factorial plus 2 by 2 factorial. See, I am writing for e power 1, right? I think so. So I am writing here x. If I have here x, get x square. Next, x cube by 3 factorial plus x power 4 by 4 factorial plus and so on, infinite terms. This represents e power x expansion. So in place of x, if I substitute 1, I get e power 1 nothing but e is equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial plus 1 by 5 factorial and so on. So what we are expecting in this particular cases. Next we go to the problems. So before going to the problems, few derivations they have given, limits, finding limits of different things. So formulas what we have learned in previous classes. What we learned? Limit extending to infinity 1 plus 1 by x whole power x. 1 plus 1 by x whole power x, which is nothing but equal to e. Next, limit extending to 0. Here extending to infinity we get 1 by x. If extending to 0 we get 1 plus x whole power 1 by x, which is equal to e. Limit extending to 0 e power x minus 1 by x, which is nothing but equal to 1. Limit extending to 0 a power x minus 1 by x, which is equal to log a power x minus 1 by x is equal to log a. And one more, formula, limit extending to 0 log 1 plus x by x, which is equal to 1. 1 plus x by x is equal to 1. See, these are all formulas. We have to remember these formulas. While applying this in a problem, we should make sure that whether the particular thing is 10 to 0 or not. If you want to apply formula, we should make sure the x, the denominator what we have, that should tend to 0. If we want to write in place of x as x plus 1, if they have given like limit x tending to 5, so we should make sure that limit x minus 5 tending to 0 and particular conversions, then we have to apply the formula. Directly for this, if x tending to 5, we cannot apply the formula like equal to 1. In these cases also same. So whatever the power we have, we should make it as a denominator. by suitable multiplications and divisions, and at the same time we should make this x tending to 0 as particular thing. Suppose I have e power ax minus 1 by x. So I don't have here ax. So what should do? I have to multiply this x by a, and I have to divide this x by a, which is nothing but divided by a. So I have e power x by x form, but in place of x I have ax. So both sides we multiply by a, we get ax tending to 0. So in this way, actually these are we learned in plus 1, just we are recalling these limits. We go to the problems. Tending to infinity 1 by x minus 3 whole square. So we learn limit x tending to infinity 1 by x is always equal to 0. So coming to this particular problem, I have here x tending to infinity, that's why 1 by x then it will be equal to 0. But I have x tending to infinity, I have to find 1 by x minus 3 whole square. So I have to make this limit as x minus 3 tending to. As x tending to infinity, what about x minus 3? Tending to infinity minus 3, which is nothing but infinity only, no? Infinity minus 3, which is nothing but infinity. So I can rewrite it as limit x minus 3 tending to infinity. So 1 by x minus 3 whole. So 1 by x minus 3, as x minus 3 tending to infinity, we get 0. 0 square is 0. So next problem, limit x tending to 0, cos 1 by x. Limit x tending to 0, cos 1 by x. So we have to find this particular thing. See, actually cos function is defined for all real numbers, but here I have a cos of 1 by x. So for x tending to 0, 1 by x tends to infinity, right? Now at 0, there are two cases arises. What are the two cases? If it is approaching from left side and it is approaching from right side. If it approaches from left side, what I get? Cos of minus infinity. If it approaches from right side, what I get? Cos of plus infinity. So what I get? Cos of minus infinity and cos of plus infinity. Right? But cos of minus theta, cos of plus theta both are equal to cos theta only. Cos of minus theta and cos of plus theta both are equal to cos theta only. Numerically this may equal, which are nothing but cos of infinity. But you see, I have here infinity. That value particularly we don't know, and the range of cos is fluctuates in between minus 1 and 1. So we are not getting a particular value, we are getting a value which is fluctuates in between minus 1 and plus 1, like this. The graph of cos is, right? It fluctuates in between plus 1 and minus 1. So what we can say, the limit of cos 1 by x where extending to 0 does not exist. And one more, limit extending to 0, 3 power x minus 1 by limit extending to 0, 3 power x minus 1 by root over 2 plus x minus root 2. So this is a problem they have given. So we can write the limit of f of x by g of x can be written as limit f of x by limit g of x. So that's what I want to apply for this. So I write it as limit extending to 0, 3 power x minus 1 whole divided by limit extending to 0, root of 2 plus x minus root 2. So we have learned the formulas. We can apply formula if I have a power x minus 1 by x, but I couldn't see here x, so I want denominator x. For that purpose, what I am doing, numerator and denominator both I am dividing by x. I divided by x. Further, this one conversion, numerator conversion got over, denominator conversion. So how I have to convert the denominator? So we have a formula like a x power n minus a power n by x minus a as limit x tending to a. Here x should not tend to 0, x should tend to a, what I have in this particular place. So we have to convert the denominator in that particular form. So how I can convert? I can write it as x plus 2 whole power 1 by 2. 2 power 1 by 2, there no problem. If I add 2 both sides, definitely x plus 2 tends to 2, what I have here. What about the denominator? Simple. Denominator, add 2, subtract 2. So I have added 2 and I subtracted 2. See, so what we get? Limit x tending to 0, p power x minus 1 by x, apply formula, divided by limit. For this what I did? Added 2 both sides. I get x plus 2 tending to 0 plus 2 nothing but 2. So I get here 2 plus x whole power 1 by 2 minus 2 power 1 by 2 by, so what I did? Added 2 and I subtracted 2. I get 2 plus x minus 2. So what is the formula for exponent minus a power n by a? N into a power n minus 1. For this limit x tending to 0, what we have a formula? Log a. So two formulas apply here. We get log, in place of a I have 3, base is e. Next log, so what we get? N into, n value is 1 by 2, 1 by 2 into a value is 2 power n minus 1, which is nothing but 1 by 2 minus 1. So we get 2 log 3 into 2 power minus root 2. What we get, right? In the denominator we get 2 power minus 1 by root 2, which is nothing but 1 by root 2. You can transfer it to numerator, then it becomes root 2. Final answer 2 root 2 into log 3. 2 root 2 into log 3. Next one. We shall see the next one. The next one. X minus 1 by log x. X tending to 1. Limit x tending to 1. X minus 1 by log x. Right? So I have to convert this one in the form of logarithm. So in logarithmic, what relation we have? Log of 1 plus x by x. 1 plus x by x. Right? So I have here x minus 1. So this one I want to convert in terms of x minus 1. How I can convert? Plus 1, minus 1. Then I can make it as 1 plus x. I want 1 plus something. Something is called x here. So in place of x, what we have? X minus 1, right? And x tending to 1, we cannot apply formula for this particular case. We can apply if x tending to 0. So I have to subtract 1 both sides. Then I get limit x minus 1 tending to 0. X minus 1 by log 1 plus I want to subtract 1. I added 1 here. I subtract 1. X minus 1. So is this x as 1 plus x and denominator x? So I can rewrite it as 1 by limit x tending to, x minus 1 tending to 0 log 1 plus x. Okay, myself x means x minus 1 by x minus 1, which is equal to 1. So my answer is 1. Okay, 1 by 1, which is equal to 1. Examine the function f of x. Examine the function f of x. Given as f of x is equal to e power 1 by x for x not equal to 0 and 1 for x equal to 0. Right? So previous classes we have discussed if x not equal to 0, we just find its limit and we equate to f of. But you see here, I have a function 1 by x. 1 by x. It changes for positive values as well as negative values. You see, 1 by minus 1, 1 by minus 2, 1 by minus 3. Okay, in the same way, 1 by 1, 1 by 2, 1 by 3, 1 by 4. So what I am getting here? Minus 1, minus 1 by 2, minus 1 by 3. See, in case of negative, if the values, nothing but the denominator increases, but the value of the function f of x increases with value increase. But in this particular case, 1 by 1 is 1, 1 by 2 is 1 by 2, 1 by 3 is 1 by 3, and 1 by 4. What happens? If the value of x increases, the value of 1 by x, nothing but the value of y decreasing. So this depends whether the x values are positive or negative. So we have to go for two cases. What are the two cases? Limit x tending to 0 plus and limit x tending to 0 minus. It's not just for limit x not equal to 0 one case and x equal to 1, x equal to 0 other case. Right? Limit x tending to 0 plus e power 1 by x is equal to. So e power 1 by x, we get limit x tending to 0 plus, I substitute near to 0. So what I get? Nothing but infinity, positive. E power plus infinity. What I get? E power plus infinity. Right? Something, e value is always greater than 1, no? So what is the value of e? So I thought of discussing that. The value of e always lies in between 2.7 and 2.8. 2.7 and 2.8. So value approximately given as 2.71828. This is the approximate value, 2.71828. But actually its exact value we couldn't find. It lies in between 2.7 and 2.8. Now a value is more than 1. For infinity, rises to infinity, we get plus infinity. Now you check for e power x tending to 0 minus 1 by x. Then what we get? E power minus infinity. What we get? Minus infinity. So e power minus infinity gives 0. Why e power minus infinity gives 0? E power minus infinity is nothing but 1 by e power infinity, which is nothing but 1 by infinity is 0. See, right limit and left limit both are not equal. Therefore, at 0 we can say the given function is discontinuous. Right? Derivatives of exponential as well as logarithmic functions. How the derivatives of exponential and logarithmic functions acts. Suppose I have a function like a power x or e power x. First I find for exponential function e power x, natural logarithms, right? So I consider the function f of x as e power x. From the definition, what we can write? F dash of x is equal to limit h tending to 0 f of x plus h minus f of x by h. Right? So I get limit h tending to 0, x plus h represents e power x plus h minus e power x by h. Now limit h tending to 0, e power x plus h, how can I write? E power x into e power h minus e power x by h. So which is equal to limit h tending to 0. I can take e power x common. I get e power h minus 1 by h. So just now we have learned the limit of e power h minus 1 by h as is tending to 0 is nothing but 1. So we get e power x. E power x is not e power x does not depends on h because we are finding with respect to h. Next one, logarithmic function. Logarithmic function. If I consider f of x as log x, natural logarithmic function. Now f dash of x, as for our definition, we write it as limit h tending to 0 log f of x plus h, nothing but log x plus h minus log x by h. Okay, now limit h tending to 0, log m minus log n, which is nothing but log m by n. So I get log x plus h by x whole divided by h. Now we just divide x by x is 1 plus h by x. So limit h tending to 0, log 1 plus h by x by h. See, for logarithmic we just discussed about its limit. Log 1 plus x, in place of x what we have, that should be in denominator. I have here h by x, I should get h by x. So I got h by x, but it changes the value, that's what I have to multiply by x also. So I multiply and divide by x. Now h tending to 0, then definitely h by x also tends to 0. Now what we get? This particular thing value is 1, so 1 by x. So what is that? 1 by x. Now we just go with a power x and logarithm for any different basis. Now the function f of x is given as a power x. So previously we have discussed a power x can be written as e power log a power x. So here base and base of exponent are same, then we get nothing but a power x. Now I am finding its derivative. So d by dx of a power x is nothing but d by dx of e power log a power x. So just now we found d by dx of e power x is e power x. So we get e power log a power x, but it is not x. Definitely we have to do its differentiation. So d by dx of log a power x. Now e power log a power x is nothing but a power x. D by dx of log a power x can be written as x into log a, where log a is constant, we can take it outside. So a power x into log a. Now d by dx of x is 1. So what is the derivative of a power x with respect to x? A power x into log a. Now if the function f of x is equal to logarithm of x to any other base, if its base is not e, if its base is some 10, some 5, some 4, some 6, some root 2, then what we have to do? So we can rewrite this one as logarithm of x by logarithm of a. So previous class we learned the formulas like log a base b can be written as log a by log b for some base c. So here that some base I consider as e. So if I didn't write e, it represents the base is e. Now 1 by 8 is a constant, log a base e is a constant, so I take it as log a base e into d by dx of log x. Just now we found which is nothing but 1 by x. Now what is the derivative of log x to any other base? Nothing but base a is 1 by x into log a. So now we can find out f dash of x for f of x as log modulus of x. Base is e. I didn't mention, then it is e. So f dash of x, so if I fill this one as x, my answer is 1 by modulus of x. But it is not x, so I have to differentiate modulus of x with respect to x, which is nothing but x by mod x. So what we get? Mod x into mod x, x square, x by x square, which is nothing but 1 by x. See, so whenever we are writing this modulus of x, the function f of x as log x and f of x as log mod x. The logarithmic function is always defined for positive numbers. Okay, so if I write here x, I should mention x greater than 0. If I write like mod x, I should mention x not equal to 0. except 0 it exists. We can take any real number except 0 because modulus of any real number is always positive. Now in next class we discuss problem based on these particular formulas. So you all have to learn the formulas thoroughly for the next class.